Hello friends, welcome to this session of lecture. So in this session we will study a supercritical fluid. So it is a dense fluid which is obtained by compressing a gas. It is a dense fluid which is obtained by compressing a gas above its critical temperature, and this gas is actually called as supercritical fluid. Actually this is not a fluid. It is not a fluid, but its density is similar to that of liquid. These are some properties. It is not a gas. Why? Because of high density, and it is not. And this critical fluid has no distinct surface which separates it from the vapor phase. So there will be two states. Liquid and vapor will be all the time. So we cannot have any distinct surface also. And this fluid can be used as a solvent. The fluid of carbon dioxide is used in the extraction of caffeine from the coffee beans. So one application of this critical fluid of carbon dioxide is to extract caffeine from the coffee beans. So these are some properties of the supercritical fluid. You can see from this graph also. So this is the graph of this supercritical fluid of carbon dioxide. So this is the critical point. So critical point where the three phases mix together. That is the critical temperature, critical pressure, and the critical volume. And this is the coexistence curve, means one phase is gas, one phase is liquid. So if you go above this phase, so this is your area which is called as the supercritical area. Means if the temperature and the pressure of the substance are both higher than the critical temperature and the critical pressure for that substance, the substance is defined as the supercritical fluid. So this is the pressure temperature phase diagram. Let us see some application of the supercritical fluid. So one application I discussed, like the extraction of the caffeine from the coffee beans. In cosmetic industry, antioxidants such as polyphenols, carotenoids, tocopherols, so which is nothing but the vitamin E, so which are found in wide varieties of fruits and vegetables, like beta carotenes in carrots, lycopene in tomato. They are selectively extracted using supercritical carbon dioxide. Next, supercritical carbon dioxide is a good plasticizing agent because it can reduce the glass transition temperature. So there is transition temperature in which the glass is converting. So it reduces that transition temperature, and also it improves some properties of the polymers, like resistance, thermal stability. So this is the some of the use of the supercritical carbon dioxide I have given you. Besides, it has immense use, so that is not in our course, but it has some important uses. Now we will see how to liquefy gases. Liquefaction of gases. So already we have seen the NDU experiment, that how to liquefy the gases. So what are the principles involved in the liquefaction of gases that we have seen during the experiment done by the NDUs on carbon dioxide? So gas must be at or below its critical temperature. So lower the temperature below critical temperature, easier would be the liquefaction and less pressure is required. So this is the one point we have seen. So below the critical temperature at critical temperature, it is easier to liquefy the gases. Second, the gas is either cooled by doing external work or by expanding against the internal force of molecular attractions. So this is the second point in which we can cool the gas by expanding against the internal force of molecular attraction. So let us see how we are doing all these things. Low temperature or cooling gas may be attained by following techniques. How we can reduce the temperature? So these are the techniques. One is the using of freezing mixture. Second, cooling by rapid evaporation of the volatile liquid. Third, we can cool by Joule-Thomson effect. And fourth, we can cool by adiabatic expansion involving mechanical work. Fifth, we can cool the gas by adiabatic demagnetization. So let us see one by one. First, use of freezing mixtures. How with the help of freezing mixture we can liquefy gases. Freezing mixture means ice with various salts, or you can use solid carbon dioxide plus ether, alcohol or acetone. So this will help in decreasing the temperature. How temperature is decreased down? You add salt in water. So what will happen? The two process. the melting of ice and dissolution of salts. These are the endothermic process. Melting of ice and dissolution of salt is the endothermic process. So endothermic means very clear. Clear is that they will absorb heat. So what will happen? The temperature of the mixture progressively decreases and continues up to a temperature where the solutions become saturated with respect to salt and ice, and this is the lowest temperature. So this is the one application which was used by one scientist called Faraday. So he liquefied large number of temporary gases. Already we have discussed which are temporary gases, like ammonia, like sulfur dioxide. Why? Because these gases have low critical temperature and temporary gases, but some gases because they have low critical temperature, so which cannot be liquefied. No, this is your permanent gases. So there are some permanent gases which have low critical temperature which cannot be liquefied, but there are so many large number of temporary gases like sulfur dioxide, carbon dioxide, which can be easily liquefied. So Faraday was using this freezing mixture to cool the gases. Second is cooling by rapid evaporation of the volatile liquids. So in this method, an easily volatile liquid is rapidly evaporated to cool and liquefy less volatile liquid. So this is used for liquefaction of oxygen. So this technique is used for the liquefaction of oxygen by using the volatile liquids. Third is cooling by adiabatic expansion involving mechanical work. This means whenever a gas is allowed to expand adiabatically, it suffers a loss in its temperature. So this is concept is taken from the law of thermodynamics. We have to expand gas adiabatically, means we do not need to add heat. Adiabatic means internal heat is utilized, no external heat is supplied to the system. So first law of thermodynamics says that Q is equal to delta U minus W. Delta U is the internal energy, this is the work done. So under adiabatic condition, Q is 0 because we are not adding heat. This is the adiabatic conditions. So energy is not added. So what will happen then? Internal energy is equal to W. Or we can say subjecting a gas to do work against external pressure, a part of its internal energy is used up in doing work, and a decrease in temperature of gas is noticed. So some part of energy is doing work, and suddenly what happens? Temperature of the gas is noticed, it is decreased down. So that is work is done by the gas under adiabatic conditions on the cost of its internal energy. So internal energy is due to internal energy, what happens? Temperature of the gas is lowered and some work is done. So when you decrease the internal energy, so some work is done due to which temperature of the gas is lowered, and this principle is used for liquefaction of air.